Now, we are going to focus on a concept of experimental measurement technique which is very important in fluid mechanics called venturi meter, right? The whole concept of venturi meter in fluid mechanics lies on a very simple concept of converging area, right? A constriction. Now, just to give a very simple example, right? This is a entrance of a mall, any typical mall, right? And inside there is some big discount mela happening, and thousands of people have got the information about it that, oh, there is some great discount which is there. So everyone is rushing into the mall, right? Some people are coming from direction 1, some people direction 2, 3, and everyone is confused what is happening. Now, the cashier here has to estimate roughly how many people he will have to deal with today because of this big discount. So he has to literally measure people, like how many people are coming, what is happening. So he tells the guards here that, boss, do the following. When somebody comes, just take a signature from them and just pass me the information that, okay, so many people have come. It works quite okay for some time, and then few people come and this guy gets some information. But as the time progresses, many more gates are required to be opened, and all of these people get confused. Some guy is coming and then crossing back, right? One guy goes and crosses this, gives a signature, again comes back, again does all of that, right? So it's a full chaos. This guy then says, let me do the following. Let me shift my office and sit here. Nobody, because there is no cell at any other place, wants to go these outer directions. Everyone is just flooding, right? So whatever all the chaos those people were doing before the entrance or at the entrance dies down, and everybody follows a nice uniform stream. So this guy now has a clear understanding how many people are literally crossing my desk here, and therefore how many do I expect to serve. That's the exact perfect example of venturi meter. Imagine people being replaced with the fluid flow lines and this cashier being your meter conversion area, right? So very simply, what you have done is you have made a flow get confined in a constrained area and then use that area as your approximated measurement equations. So therefore, your venturi is typically denoted something like this. This is that venturi. This is A2, area. This is the entrance area, A1. Why did we do it? Because the flow upstream may have certain vorticity, may have certain non-uniform characteristics, non-streamlines. We have got rid of them. Once this picture is clear as to what is venturi meter, we just need to apply a very simple set of equations that we have been learning throughout in chapter 1 to 7 and just apply them here. We have learned one thing which is called continuity equation, right? What did it tell us? Rho AV equal to constant. Now, most of the times venturi meters are used for incompressible flow. There are applications where correction is made for compressed flowing, but most of the times they are used for non-compressible flow. So your rho remains constant, and because of which across the venturi meter duct, you can say A1 V1 equal to A2 V2. Right? So the conservation equation is applied. Second thing, what you do is, you know that momentum is also getting conserved. Venturi meter is a passive device, which means no energy ideally is extracted, no energy is added. That also tells me a fact that the momentum has hardly any loss. Right? So A1 area, right? The area modulus here has a conservation equation, rho V square. What did I just write? I wrote Bernoulli's equation, right? Because the flow is incompressible, I have this luxury. Okay? My whole objective is to estimate the mass flow rate. How many people are crossing the mall, right? What is the mass flow rate? What is meant of? Rho AV or rho A1 V1, which means by tapping this pressure point here at the venturi, the delta piece, right? Because pressure is a quantity which is beautifully estimated on a dial gauge. So a differential pressure which I can tap from these areas will give me indication of mass flow. And how is this through equations? So now, what will be P2 minus P1 or simply delta P? It should be simply rho by 2 V1 square minus V2 square. Just LHS RHS equations. I have to substitute this, right? Because area ratio is something which is my design constant. I know what my venture is, so I know what areas are. So it's a given thing, it's a given parameter. Some people introduce eta as A2 upon A1, the coefficient of constriction, but we will come to it, right? Just be sure to understand this term. If I now substitute A1, V1 and A2, V2 in this equation, I can also say my V2 is this, right? So A1 upon A2 into V1 is V2, right? So delta P is what? Rho by 2 V1 square, right? V2 square is common. 1 minus A1 by A2 whole square, right? What does this tell me? V1 square is simply a function of pressure type reading, density and this area ratio. So now I can go and take credit here, right? So V1 square is 2 delta P upon rho 1 upon 1 minus A1 square. So I can simplify this like this. So this is my V1. Now I can substitute this V1 in rho AV equation, right? What will I get? I will simply get m dot equal to rho A1 into square root of 2 delta P by rho A2 square upon A2 square minus A1 square. That also tells me the fact that now A1 can go inside and become A1 square here, and rho will appear in the numerator. Which means, if I know my fluid property rho and I know the pressure tapping reading from this venturi, I can estimate the mass flow rate in terms of eta. Now that's the last part, right? All I have to do is substitute this. So I will take this in the denominator, because this numerator which means is in the denominator is 1 upon A1 square A2 square, just algebraic manipulation. That also tells me the fact that m dot is 2 delta P times rho, and what is this area? 1 A2 square gets cancelled, so 1 upon A1 square minus 1 upon A2 square. It's that simple relation. So now if I substitute eta, which is typically a ratio used, I can substitute A2 as eta times A1. But what do I know? I know this area of constriction. In a flow, the area A1 may sometimes be real area or weighted sorope area. Because as we have seen in our propulsion, when you have been facing in front of engine, the cowling effect takes air from slightly outside as well. So this A1 is not exactly the same. So therefore, A2 is a better handle to substitute, right? A2 is known. So what is A1? A2 upon eta. So A2 square into eta square. So if you substitute this, you get this relation. Or simply m dot through venturi meter is 1 upon A2 root of 2 delta P into rho, denominator is nothing, eta square minus 1. The important idea here is, smaller the mass flow rates that you want to measure, smaller the eta has to be. More and more constriction, but as you start constraining your venturimeter too much, non-linearity effects come, which means venturi has a range of m dot in which it works linearly. Moment you cross that range, moment you want to measure very low mass flow rates, this technique is redundant. That's the experimentation part of it, right? Second experimentation part is the delta P tapping. More the sensitive your pressure differential reading is, better the mass flow readings that you get. If your delta P has an error, m dot also has proportionality. Third is A1, the E2, right? As you make A2 smaller, the error in 1 upon A2 keeps going up. So the three factors that govern your accuracy are range of mass flow, lower or larger which your data might needed for, the sensor accuracy in which the delta P is being measured, and A2, the least area itself in the venturi meter. Better the handle you have to eliminate these capillary effects or the ranges of lower constrictions or the pressure errors, better accuracy you will get in MROD. That's all about a venturi meter, which is a very important tool in aerodynamic experimentation measurement.